All right, section 5.1, angles of triangles, okay? If you remember, way back in chapter 1, I dug out some chapter 1 notes, we talked about a polygon. A polygon, again, is a closed plane, meaning it's on a plane, it lies in one plane figure, made up of segments that connect at their endpoints, and we call those endpoints vertices. And we had all these different types of polygons. We had ones with 3 sides, 4 sides, all the way up to like 12 end sides. Okay, in chapters 5 and 6, we're going to focus on just the 3-sided polygon, which we call a triangle. So a 3-sided polygon we call a triangle. We're basically going to focus on those triangles in chapters 5 and 6. Okay, so first we need to classify. Classify a triangle by its sides and by its angles. So classify is a way to describe or group these triangles, meaning how can I describe them? Okay, so like as a person, I could classify you. I could classify you by your hair color, blondes, brunette, which group do you fit in? Okay, I could classify you by your height, by your age, by your gender, boy or girl, by the grade you're in, by the number of freckles you have. I could classify you by a lot of different ways. Triangles aren't that complex. There's really only 2 ways of classifying them. We can classify them just looking at their sides. So this has nothing to do with the angles that are made. It's what are the lengths of the sides. Okay, if all the lengths of the sides are different. Okay, so to mark here that they're all different, I'm going to put different notches. So if I put 1 notch here, 2 here, and 3 here, that shows me that none of these sides are the same. So if it has no congruent sides, okay, no congruent sides, then we call it scalene. So no congruent sides. Okay, so if none of the sides are equal to each other, then we say it's scalene. Okay, if 2 of the sides are equal, so if we have 2, so we'll mark these 2 each with 1 notch, this one with 2, showing that's different. So if it has at least 2 congruent sides, okay, then we say it's isosceles, okay? But this at least part here, there's still some debate. There's really 2 definitions of isosceles. Some people say at least 2 congruent sides, meaning it could have more. It could have 3 congruent sides, and we could still call it isosceles. And so these words at least, some definitions include them, some do not. It depends on the country, the type of textbook, and what they use. Okay, so in this book, they say at least 2 congruent sides, but you might Google it and it'll say exactly 2 congruent sides. Okay, and the reason that this at least is a bit of some controversy is with at least 2 congruent sides, if all the sides are congruent, like in this one here, we could then also call this isosceles because it has at least 2 congruent. Okay, but to be more specific, we call it equilateral. Equilateral has 3 congruent sides. And anytime I call something equilateral, that means all of the sides are the same. So I can have an equilateral pentagon. It means all 5 sides, pentagon having 5 sides, all 5 sides are the same. So whenever we use equilateral, equilateral just means all sides congruent. Okay. So equilateral isn't just for triangles. We use that word for other polygons as well. Okay, whereas isosceles, at least 2 congruent sides, scalene, no congruent sides. So again, that's just looking at the sides. I didn't pay any attention to any of the angles that were made. Okay. All right, so that's one way of classifying triangles. I can classify them just by looking at their sides. I could also classify them just by looking at their angles. Okay, if all 3 angles are acute, okay, if all 3 angles here, if all 3 of these were acute, then we call the triangle acute. So it has 3 acute angles. So if all of these angles, 1, 2, 3, all of those angles are less than 90, then it's an acute triangle. Okay. If one of the angles is right, then we call it a right triangle. So it has 1 right angle. And if you notice just that 1 right angle, the other 2 angles are acute. So it has 1 right and 2 acute angles. We'll put that in little letters below. So it has 1 right and 2 acute. Okay. For an obtuse triangle, if it has 1 obtuse angle, then we call it an obtuse triangle. Okay. So if it has one obtuse angle, we can call it an obtuse triangle. Okay. And there's also a special name for an acute triangle that has all angles the same. If all of these angles are the same, then we call it equal angular. Okay, so that means it has 3 congruent angles. Okay, and that's really equal angular always means all angles congruent. Again, just like equilateral up here, equal angular we could use for a lot of different shapes. Like I could have an equal angular hexagon. It means all the angles are the same. All angles congruent. Okay, so we can classify a triangle by its sides and by its angles. Okay, so here, this example says classify the triangular shape of the support beams in the diagram by its sides. So if we're going to do it by its sides, we'd use the words scalene, isosceles, or equilateral. Okay, and by measuring its angles. So we might need our protractor here to measure a couple angles. So if we're measuring it by its angles, we would call it acute, right, obtuse, or equal angular. Okay. So if we look at our sides, it actually gives us the notches. If you notice, this has got one little red notch in it, this has one little red notch in it, but this has none. So I know I have at least 2 sides congruent, so we would call it isosceles. So this triangle is isosceles. Now, by measuring its angles, if we come in and we measure, they don't give us any marks for these, so we're going to have to measure them. This one looks like it's, let's see here. Here's my 0, so 10, 20, 30, 40, 55. So that one looks 55. Okay, so this angle here is 55 degrees. Okay, now let's come over and let's do this other angle down here at the bottom. So this angle here is, so we're pointing now at this 0, the outside 0. So we go up 10, 20, 30, 40, 50. That one looks like 55 also. So this angle here also looks like 55. So far we're looking acute, but now we need to do this top angle here. Let's double check that, guys. So put that right on that point right there. Okay, so we are lining up that point right there at that vertice. We're shooting out this way. So we're looking at these inside zeros. I'm going to use my ruler to get the other line. So it looks like we're the 0, so 10, 20, 30, 40, 50, 60. Looks like maybe a 70-degree angle. This one here is maybe 70 degrees in there. So they all look, they're all less than 90, so this makes this an isosceles acute triangle. Because all of the angles, it has 3 acute angles, and 2 of the sides are the same. So it makes it an isosceles acute triangle. So a triangle can be both isosceles and acute. Just like you can have both brown hair and be 15. You can be more than one thing. A triangle can be one of these and one of these. A triangle is always one of these or one of these. Okay. All right, next. Classify the triangle by its sides, then determine whether it is a right triangle. Okay, so first of all, I don't know the length of any of these sides. So I don't know if they're the same. I can tell this one's obviously shorter than these two. So it's not equilateral. So I know it's not equilateral. But I can't entirely tell if it's isosceles or not because I'm not sure if these are the same distance. So we're going to find those distances. I'm going to find the distance from P to Q. Okay, and I'm going to find the distance from O to Q. To find those distances, I'm going to have to use the distance formula. Well, let's write that down in case we don't remember what it is. Square root of, it's on a poster in my room if you don't remember. Subtract the x's, square it, plus subtract the y's and square it. Okay, so subtract my x's from P to Q. So we'd go -1 minus 6 squared plus 2 minus 3 squared. Okay, so I'm going to do all of that part in my calculator here just to save some time. So parentheses, -1 minus 6 squared plus parentheses 2 minus 3 squared. I get 50. So this is the square root of 50. Okay. Now, if O to Q is the same thing, then I know it's equilateral. Okay, so O to Q. So we're going to 0, minus 6 squared plus 0 minus 3 squared. So let's go 0 minus 6 squared plus 0 minus 3 squared, 45. So hence not isosceles either, because those are not the same thing. So this means this is scalene. So it says classify the triangle by its side, so we did, it's scalene. Then determine whether it is a right triangle. Well, if it's a right triangle, the only angle that looks somewhat right, that looks way too small. That's acute. This one looks pretty small. But to make a right angle, again, a right angle, if two lines intersect to make a right angle, that also means perpendicular. Remember what perpendicular means? Perpendicular means they intersect to make a 90 degree. And I know perpendicular lines, if you remember, have negative reciprocal slopes. So let's find the slopes of each of these lines. So here, let's find the slope from 0 to p. Rise up 2, run back 1. So now we're finding the slopes. So the slopes of segment OP is rise up 2, back 1. So up 2, back 1. So that would be negative 2. Okay, so that's from O to P, segment OP. Now let's do segment PQ. Let's find the slope of that. So from P to Q, rise up 1, run 1, 2, 3, 4, 5, 6, 7, up 1 over 7. So from P to Q, it's 1/7. Well, we don't have any negative reciprocals there. So now last one, we need to do O, Q, O, Q to O, or O to Q. I'm going to do O to Q instead. It goes up 1, 2, 3, over 1, 2, 3, 4, 5, 6. Rise is up 3, run is over 6. 3 over 6 simplifies to 1/2. Well, this is negative 2 over 1. Well, looky there. Those are negative reciprocal slopes. So that tells me that the segment from O to P and from O to Q are perpendicular, which means there's a right angle. So then determine whether it is a right angle. Yes, it is a right angle. Yes, it is a right angle because it has a right triangle. It's a right triangle because it has a right angle in it. So it's scalene, and yes, it's a right triangle. Okay. All right, I talked about this a little in the exploration. Hopefully you did that first. Okay, triangle has 3 interior angles. Interior meaning inside. Okay, so it has 3 interior angles. So it has the angle formed right here. So it'd be that little angle right there. This one here, that angle, and this one here. So they're marked in orange. There's those interior angles. So we have these 3. So we have this angle, that angle. Okay, but I can also make exterior angles by extending out a side. So I'm going to label these points A, B, and C. So I'm going to take the segment AC and I'm going to extend it out here towards C. Okay, so if I extend that out, I've actually created this angle out here. Okay, so I've got that angle right there, that's C. Okay, and I can take here B, so I extended C out there, so I can do the same thing with B here. I can take B and extend it out that direction. So then I've created this exterior angle right here, this one right there, okay, at B. And then I can do the same thing here at A. I can take BA and extend it out this direction. If you notice, each side is only extended out one direction. Okay, so we only have one exterior angle at each point. So there's another exterior angle, and so we get those exterior angles. Okay, so if you noticed in our exploration, and you did discuss this in Algebra 1, if you remember, if I take all of the interior angles of a triangle and add them all up, hence the sum, again, sum is the result when you add, then you end up getting a sum of 180 degrees always. So if I take, in this case, the measure of angle A, this angle here, add the measure of angle B, add the measure of angle C, you get 180. Regardless of the type of triangle, you will always get 180. Okay, I think that's pretty remarkable. Okay, and we're going to look at actually a proof of that theorem. Okay, to prove certain theorems. Okay, this might be a good proof to know, so you might want to put a star by this in your notes. But to prove certain theorems, sometimes you need to add a line or a segment or array or something to the picture to be able to prove it. We call that an auxiliary line or an auxiliary segment or an auxiliary ray. So in this theorem, in this proof here of this theorem, we're going to actually draw an auxiliary line in. Okay, so we want to prove measure of angle measure of angle 1 plus a measure of angle 2 plus a measure of angle 3 is 180. Okay, given we have this triangle. Okay, to do that, we're going to draw in an auxiliary line. So first we're going to take line AC, segment AC, and we're going to extend it. Okay, and then we're going to come up here and we're going to draw a line parallel to AC that goes through B. Okay. So there's our auxiliary line right there. So it was a line not originally in our picture, but we're going to draw it in. And we're going to put a point D out here that we'll use later. And the reason we like that D is so that we can talk about this angle right here. Okay, that angle D. Okay. All right, so our first plan, our plan here, we're going to write a plan out, is again, we're going to draw auxiliary line. Line BD, so that it's parallel to line AC. Okay, so because then now what we end up having is we end up having parallel lines and transversals. Okay, so I can go ahead, if I extend line BC out, here we have parallel lines and a transversal, so we can use our corresponding angles, alternate interior angles, and all that type of thing. Okay, so let's go ahead and let's label in, let's call this angle 4 and let's call this out here angle 5. Okay, so, so our next plan, again, our end goal is to prove that 1 plus 2 plus 3 is 180. Okay, but I know 4 plus 2 plus 5 is 180 because they're all on one line here. So we know 4 plus 2 plus 5 is 180. So we know angle 4, this is just our plan. Angle 2, angle 5 is 180. Because of why? How do we know that? The angle addition postulate, definition of straight line, however, the angle addition postulate, or we could use just the definition of a straight line, definition of straight angle. We know a straight angle adds up to 180. Okay, so one of those two. So we know 4 plus 2 plus 5 is 180. But we also know that given our transversal here, we know that angle 3 is congruent to angle 5, alternate interior angles. So we also know angle 3 congruent to angle 5, alternate interior angles. Okay, and by that same definition, we can use angle 4 if we use this transversal, extend this transversal out. Okay, angle 4 and angle 1 are also congruent by the same reason. Well, so that's the same reason. They're congruent because of alternate interior angles. Well, if they're congruent, then I know their measures are equal. So I know the measure of angle 3 equals the measure of angle 5, and the measure of angle 4 equals the measure of angle 1. Definition of congruence. Again, this is just our plan, so it can kind of be sloppy and all over because of the definition of congruence. Okay. But up here, I have 4 plus 2 plus 5 is 180. Again, our end goal, 1 plus 2 plus 3 is 180. Okay, I can replace the 4 with the 1 because measure of angle 4 equals measure of angle 1. So I can come in here and replace this 4 with this 1 because they're equal. Okay, I can also replace this 5 with a 3 because they're equal. So then basically I have measure of angle 1 plus measure of angle 2 plus measure of angle 5 is 180. So I've proven it. Okay. Okay, so now what I want you to do is I want you to pause the video and fill in, okay, your statements and reasons here. Okay, so go ahead and fill in reason 1 from our plan here. Okay, from our plan. Okay, when you're done, open your book to page 234. Top of the page actually has this proof, so I want you to double check your statements and reasons there. Okay. All right, our last theorem, I believe it's our last theorem for today, oh, yep, last theorem. We have one other little corollary. Our exterior angle theorem. The measure of an exterior angle of a triangle. So if I was to go ahead and, again, extend out my side here. Let's go ahead and let's extend out here. So the measure of an exterior angle triangle is equal to, so the measure of this angle, let's put a D out here. So the measure of this angle, measure of angle DAB, so this angle right here, is equal to, the sum is equal to the sum, that's adding, of the two non-adjacent interior angles. So if you notice, this angle right in here is adjacent because it shares a side. It shares this side. That side is on both of those angles. So this angle is the adjacent one. The non-adjacent would be these two over here. This guy and this guy are the non-adjacent sides, non-adjacent angles. Okay, so if I add those two non-adjacent angles, it equals the sum of this one here. So if I add the measure of angle B plus the measure of angle C, if I add these two, I get this. And you should have noticed that in our exploration that you did. Okay. So I can use that to actually find missing pieces of triangles. So here they want me to find the measure of angle JKM. JKM. This one out here. So I'm looking for this angle. Well, the measure of angle JKM would be equal to the sum of the measure of the non-adjacent. Again, here's my adjacent one right in here, the one right next door. So I would have to add these other ones, the measure of angle J and the measure of angle L. But I know the measure of angle JKM is 2x minus 5. I'm just replacing here. The measure of angle J is x. The measure of angle L is 70. So now I have a nice equation to solve. Okay. I'm going to start by subtracting x from both sides. So I get x minus 5, and then I'm going to add the 5 to both sides. So x equals 75. So we know x equals 75. The measure of angle JKM right here is 2x, so 2 times 75 minus 5. So 2 times 75 minus 5 is 145. So the measure of angle JKM is 145 degrees. Okay. All right, now we have a corollary to a theorem. What the heck is a corollary? A corollary is just a statement, okay, that can be easily proven using a theorem. Okay. So a corollary is really attached to a theorem. So we had our triangle sum theorem, where our triangle sum theorem, again, was triangle sum theorem. The sum of the measures of the interior angles of a triangle is 180. So when you add up all the angles, you get 180. Okay, if I was to take that and go one step further, hey, then we know if one of the angles is a right triangle, if one of the angles is right, so this angle is 90 degrees, and if I know if I add them all up and get 90 degrees, that means A and B together have to be 90 degrees. But we know if two angles add to be 90 degrees, it means they're complementary. So if I have a right triangle, the other two angles that aren't the right angle are complementary, and that just comes from that triangle sum theorem. Okay. So here for example 4, the measure of one acute angle of a right triangle. So we have a right triangle here. So this angle is our 90-degree angle. The measure of one acute angle of a right triangle is 1.5 times the measure of the other acute angle. Find the measure of each acute angle. So I don't know what either of these are, but I know whatever one is, let's use x. The other one is 1.5 times that. So that means this one would be 1.5 times that x. Okay. And using our corollary to the triangle sum theorem, the acute angles of a right triangle are complementary. I know these two angles are complementary. So I know that they have to add up to be 90. So I have x plus 1.5x, so that's 1x. Plus 1.5x gives me 2.5x is 90. Divide both sides by the 2.5. x would be equal to 90 divided by 2.5 is 36. So that tells me that this x here is 36 degrees. So this other one, it says find the measure of each acute angle. So this one would be 36 times 1.5, 54. So 36 degrees and 54 degrees. Okay. Which makes sense because when you add those, 36 plus 54, you get 90. So there's two angles. Okay, so I want you to go ahead and write down the practice down here at the bottom of your page. Sorry for the lengthy video, there was just a lot in it. Hey, and good luck on your practice. See me if you need help.